So yesterday, we went over Newton's first law. Newton's first law applies to all situations where the net force is what? Zero. Okay? In any net force is zero situation, the acceleration of the object will also be zero. Okay? So Newton's first law governs situations where an object is at rest or is traveling at a constant velocity. Newton's second law deals with the other situations. That is where there is an unbalanced or net force, and as a result, there is an acceleration. Okay, so mathematically, Newton's second law is very simple. 3-variable formula. Okay, F net is mass times acceleration. All right, so we often write it like this. Instead of just saying F, we say F net equals mass times acceleration. Now, yesterday, we also learned that net force is something else. Not only is it mass times acceleration, it was also, anyone remember? We added stuff together to get it. The vector sum of all forces. Okay, so there's actually two ways to calculate net force. It's the vector sum of all forces, or it's the mass of the object times the object's acceleration. In 95% of all Newton's second law problems, you will have to use both methods. Okay, like initially, maybe the question tells you, the acceleration of the object is this much, its mass is this much, friction is acting with this many newtons, how much force is pushing the object forward? All right, and so you'd have to use mass times acceleration to get the net, and then figure out what the missing force is. Or the question gives you all the forces and the mass and asks you to calculate the acceleration. So you have to add all the forces together and then find the acceleration of the object. Okay? In the end, they basically all break down to one of those two situations. Okay. All right, so for Newton's second law, the big things here are understand the relationship between force, mass, and acceleration within F equals m times a. Okay? Understand how force and mass influence change in velocity, okay? And solve problems related to Newton's second law. Okay, so second law deals with what happens when there is a net force acting on an object. So it's the opposite of Newton's first law. Okay, again, think about the hockey puck. Okay, when a player strikes the puck, he causes the velocity of the puck to change. That is, the puck accelerates. Okay, the cause of the acceleration is the force that the stick applies. Everybody with me there? Okay, without that force, the puck wouldn't do anything. So as long as that force acts, the velocity increases. We talked about that yesterday when we talked about how the material that they make sticks out of now has helped to improve the application of force. So the greater the force, the greater the acceleration. So this has to do with one of the key points that we just looked at. Okay, we have to understand how force and mass influence change in velocity and their relationship. So this is talking about that. Okay, so the greater the force, the greater the acceleration. Right? And that should make sense. I mean, if we're looking at this formula, F equals m times a, if I'm solving for a, that would mean F divided by m. So yes, if the force gets bigger, a should get bigger. Agreed? Okay. If I double F, what happens to a? It will double. I mean, provided m stays the same. Right? If I double the force, I double the acceleration. That's a what kind of relationship? It's linear. Yeah. Okay. So force and acceleration have a linear relationship. If I double the force, I will double the acceleration. Okay. And conversely, double the acceleration will require double the force. Okay. All right. So the force and the acceleration act in the same direction, and they have the same vector. Right? I mean, looking at this formula here, if the object is accelerating to the left, then the net force has to be left. Otherwise, it's not going to move that way. Right? So the force and the acceleration will always have the same vector. Okay, so that's also an important one to make note of. Okay? And the greater the force, the greater the acceleration. All right, questions so far? All right, so lots of times more than one force acts on an object. Okay, and we talked about free body diagrams right at the end of the period yesterday. So a free body diagram allows us to basically figure out which forces are acting and diagram which way they're acting to give us at least an idea or a picture in our mind of what the situation looks like, right? So when we're looking at those forces, like for example, this very simple free body diagram here, right? I have force 1 and I have force 2. Force 1 looks like it's a little bit bigger than force 2. So there is a net force, and it's which direction? To the right, okay? Because F2 is bigger, all right? So that means that that little black box is going to accelerate towards the right, okay? Because there is, again, a net force. The vector sum of all forces says there's a net force in this direction. All right. Now, in Newton's second law, okay, net force is one of only two factors that influences the acceleration. Obviously, if I double the force, I'm going to double the acceleration. But the other factor that influences acceleration is the mass of the object. Okay? And this has kind of the same relationship as mass had in Newton's first law. The more mass you have, the more inertia you have, the harder it is to change your velocity. Well, okay, bigger the mass, the smaller the acceleration is going to be. All right, so if I'm looking at these two situations, okay, in the first situation, I have this golfer who's using his golf club in an appropriate manner to hit a golf ball. Okay, he swings as hard as he can and hits the golf ball. So his force is kind of fixed. He's swinging as hard as he can. He's hitting an incredibly small mass. So that will produce a very large acceleration. Okay. Now, if for some reason he decides he's going to wind up and smoke this truck with his club, okay, he had better be willing to part with the club because it's certainly going to be destroyed, right? So he's going to, same force, he's going to swing as hard as he can, but he's now hitting an incredibly large mass, which will produce a correspondingly tiny acceleration. Now you're probably all looking at that diagram and going, that truck is not going to move. Okay? Yeah, you're probably right. The truck in the real world isn't going anywhere. Does that mean it doesn't accelerate? Okay? It's going to seem weird, but it does still accelerate. It's just the truck didn't all go together. Right? If I'm standing here at the front of the truck and I put my hand on the truck, do I know when he hits it? Even if I have like noise canceling headphones and I can't hear him, do I know when he hits the truck if I'm touching the truck? Okay. The vibration travels through the truck. That means every particle in the truck accelerated in order to pass that vibration through to my hand at the other end. Okay. He still made the truck accelerate. He just didn't make the whole truck roll or slide in my direction by hitting it with the golf club. Okay. He'll also likely change the shape of the truck. He's going to put a dent in it. Okay. That counts too. That's an acceleration. He made at least that part of the truck accelerate. Okay, so it all counts. Okay, it's not always as simplistic as, oh, the truck moved as a result of him hitting it with the golf club. Not likely. Okay, now if it was on perfectly frictionless ice, would that be different? If it was on perfectly frictionless ice, yes. And he hits that thing with the golf club, the truck will slide. Not very fast. Okay, it would be almost imperceptible, but it'll start sliding, and it'll keep sliding if it's frictionless. Because even after he's hit it, it'll now have the velocity produced by that acceleration, and according to Newton's first law, would maintain that velocity along the frictionless surface. Okay, everybody okay with that? All right, so what we have to get out of this is this. Force and acceleration have a linear relationship. If one goes up, the other goes up. Mass and acceleration have an inverse relationship. If I increase the mass, the acceleration goes down. Okay, that's what we have to understand. That's the relationship between force, mass, and acceleration in Newton's second law. Bigger the mass, smaller the acceleration. Okay, questions there? All right, so when a net force acts on an object of a certain mass, the acceleration that results, like we said, is directly proportional to the force and inversely proportional to the mass. The direction of the acceleration is the same as that of the net force. That is Newton's second law in words. Okay, so if you're looking at what is Newton's second law in words, that's it. Okay, mathematically speaking, Newton's second law looks like this. Now, if you recall, yesterday I said we're going to spend like 2 weeks on Newton's second law. It's a 3-variable formula. It's obviously not the math that's challenging here. Okay, you guys can all manipulate this. It's no different than manipulating V equals D over T. Okay, what is tricky about Newton's second law is the vector sum of all forces part. Okay, we get into a lot of situations where even identifying some of the forces involved becomes quite difficult. Okay, this is where we really have to be able to see into a situation. Okay, far more than we needed to in the first unit, where it was like, oh, well, that object's accelerating and its initial velocity was this and its final velocity was that. Okay, I can do that. Right? In this one, it's here's this object in this situation. Calculate its acceleration, and then you've got to picture that situation. You've got to draw your free body diagram, identify all the forces, calculate all the forces, add them up in a vector sum, okay, and then go. So it's actually a lot of steps. It's never just as simple as F net equals M times A. All right. Now, units for force. Okay, the units for force technically are a kilogram meter per second squared, because you are multiplying mass in kilograms by acceleration, which is meters per second squared. So the units for force are kilogram meters per second squared. But in honor of the guy that came up with so much to do with physics and forces, we abbreviate that as a Newton. Okay. But you do still have to remember that the fundamental units of a Newton are a kilogram meter per second squared. Okay. But you can always write Newtons. That's fine. All right, questions on that? All right, so that's kind of all the basic stuff to do with Newton's second law. All right, start looking at kind of situational stuff a little bit more here. All right, free body diagrams we talked about yesterday. Okay, being able to draw a free body diagram. Okay, some people draw free body diagrams like part A. We don't. Okay, it becomes very confusing when they're not originating from the center of mass. So we always draw the forces as though they originate from the center of the mass. So we would write gravity, okay, right here, and we would write the reactive or normal force, we called it yesterday, from the table pointing upwards. Okay, what's the net force in this situation? 0. Okay, those two forces are equal and opposite, thus they cancel. The object just sits on the table. Okay, so a situation like this becomes a bit more complex when we start getting into, let's say, the table is then, so it starts out flat, but then somebody takes the table and lifts up one side of it. So now the table's on an incline. Does this change some of the forces? Okay, does it change gravity? No. Gravity actually doesn't change in this situation. Gravity would act still straight down. That's the only way gravity can act, towards the center of the earth. But now that normal force that's produced by the table is going to point which way? Because before it was sitting on the table, it pointed straight up, perpendicular to the table. Yeah, so Tyler's right, it's going to go this way. The table can only push perpendicular. And now that number is not going to be the same as the force of gravity. It's going to be less. Right? It was only equal to gravity because they were directly opposed. Now it's going to be less because what's this object going to want to do? It's going to want to slide down the surface. Okay? If there's friction on this surface, then friction would go this way. Okay? So we'd have the force of friction. We'd have normal force. We've got the force of gravity. Okay? We have all these forces that are interacting. Right? So our free body diagram becomes a little bit more complex. And now we would have to draw a vector diagram. So we would say, all right, I got normal force, I've got gravity, okay, and I've got the force of friction. Okay, so my net force would be right here. And it just so happens that it's which way? Straight down the ramp. All right, so that's where we're going. We're not there yet. Okay, I'm just illustrating to you that it's not going to be as simple as F equals M times A. Okay, there's going to be lots of forces to figure out. Okay, and that kind of stuff. Okay, so it's going to get trickier than up and down and left and right. Okay, it's going to get trickier than that. All right, I want you to write this one down. and draw a free body diagram of it. Okay, they don't really have a free body diagram there, but their diagram is close. All right, so I want you to write down the question and draw a free body diagram, and then I'll walk through how we solve it. And you might be able to solve it on your own. You guys are smart. Okay, so let's have a look at this one. So we got two people pushing a stalled car, which back in the day was a far more common occurrence than it is today, because, well, cars are a little better today, and well, you can't start them by pushing them anymore because standard transmissions have essentially disappeared. Okay? It used to be that if your battery died, you just get two of your buddies to push the car and you throw it in second, pop the clutch, and it would fire right up even if the battery was dead, because you could start it on compression, which is pretty handy. You can't do that anymore. You can't do that with an automatic. You can't slam it into gear and hope that it will just fire to life. It's kind of hard on the transmission. Plus, you have to get it going like more than 30 kilometers an hour, which means you need two Olympic level sprinters to push the car. They're not usually hanging around. So, all right, here's what we got. We got the big car, okay? We're told the car is 1,850 kilograms. So to draw our free body diagram, we have a box labeled 1,850 kilograms. The forces we are aware of are the two people pushing, okay? So we've got a force forwards of 395 newtons. We have a force forward of 275 newtons. And then we have a resistive force of friction of 560 newtons. Now, are gravity and normal force also present here? Do I need to draw them? No, they're going to cancel each other out. So rather than make my diagram really busy, since they're unimportant, I'm not going to put them on there. All right, so now I have all the forces that I need. And conveniently, they're collinear. So do I need to draw a vector diagram? No, okay, I mean, they're collinear, I don't need that. So all I have to do then is recognize that F net is the vector sum of all forces. So I'm going to go positive 395 plus positive 275 plus negative 560. Right, that'll give me the vector sum of all the forces. So 395 plus 275 minus 560 tells me I have a net force of positive or forward 110 newtons. All right, now that I know F net, can I find the acceleration? Okay, remember how I just said a few minutes ago that on 95% of all Newton's second law problems you would do both? Okay, case in point. All right, so F net also equals mass times acceleration. So acceleration is F net divided by mass. 110 divided by 1,850. So 110 newtons, and newtons, remember, are a kilogram meter per second squared, divided by 1,850 kilograms. So the kilograms are going to cancel, and we're going to be left with meters per second squared. Okay, not very many meters per second squared because it's not a very big force compared to the mass of the car. All right, so we're going to produce an acceleration of only 0.059 meters per second squared in a forward direction. Okay, now remember, that doesn't seem very big, but if they keep pushing, it'll add up. The acceleration won't get bigger, but the velocity will. And eventually they'll get the car moving fast enough that you could probably start it on compression if it was a standard. Okay. Everybody all right with that? I mean, it's pretty rare to see two people get behind a car and actually make it go really fast. Okay, it's hard to push a car. They're big and heavy. They have a lot of inertia. Okay, we can only, use so much force. And as you've seen often in the winter times, we get people pushing cars up the hill to get out of the parking lot because, well, it's really steep and it's always really icy. Okay, they don't really get it moving very fast. Maybe that's because they're always slipping when they push. Either way, okay, it's not going to produce realistically a very big acceleration. All right, everybody okay with how that one worked? Okay, that's about as basic as a Newton's second law problem would be, unless it was so basic that it was, here's the net force, here's the mass, calculate the acceleration. Okay, you actually had to calculate the net force here. So there was one extra step. All right, try this one. They've kind of drawn the free body diagram for you already. Okay, you would just have to label the forces, okay, like put the number of newtons on there. And they've also got, okay, a bit, I would say, don't look too much at that second diagram. All right, it's not going to be as helpful as you might think it would be. But let's see if you guys can figure out this second one with the accelerating block. I'll give you a few minutes on that, and then I'll walk through it. Okay, So let's first look at the free body diagram, because they did a pretty good job of drawing the free body diagram minus putting the forces on their arrows here. Okay, so we know that the first force is 35 newtons and it's directed 60 degrees above the horizontal, so pushing it that way. And the second one is quite a bit smaller. It's only 10 newtons and it's going straight this way. So as kind of a prediction, which way is this block going to go? Yeah, but not quite along the 35, right? Just slightly less than that. Okay, because when we draw a vector diagram of this, okay, it's going to look like this. We'll have our 35 Newton force angled 60 degrees above the horizontal. We'll have our 10 Newton force drawn tail to head. Okay, and then we'll have our resultant, which in this case is now the net force. Okay, so no different than what we did in the last unit. Okay, it's just now they're forces instead of displacements. Right, so that'll allow us to calculate the vector sum of all of those forces. Right, we're adding the vectors up. All right, so what we got to do in order to make that happen is we got to find all the x's and y's. Okay, so the black, the 35 Newton one, okay, black x is going to be the cos of 60 times 35 newtons. Okay, and the y component is the opposite side, so that'll be the sine of 60 times 35 newtons. Okay, so this should be 17.5 newtons. Okay, and I can't remember what the sine of 60 is. Come on. All right, is 30.311 newtons. Okay, so this is going to be, they'll both be positive. One is up and the other is to the right. Okay, so we got an XY scatter plot here. All right, now we should be able to find green X and green Y. Green Y is easy because only one of the vectors actually has a vertical component. So green Y is going to be 30.311 newtons, okay, upwards. And then green X, okay, we'll have to take into account the 10 newtons as well as the 17.5 newtons. So green X will be 27.5 newtons. Okay. Everybody all right with what I've done so far? Okay. The only thing that's different from last unit is these have an N on the end instead of an M. All right. Otherwise, mathematically the same. Okay, so now if I want to calculate my net force's magnitude, I will use Pythagorean theorem, and I'll have 27.5 squared, okay, plus 30.311 squared, and that will give me, okay, the magnitude of the net force. So, all right, so our net force is 40.927 newtons. Then we need a direction. Okay, so that'll be tan to the minus 1 of the opposite side, which was 30.311, divided by the adjacent side, 27.5. Okay, so we're looking at 47.8 degrees above the x-axis, because that's all we were given in terms of reference direction. Okay, so now I've got the net force and I've got the direction of the net force. What did the question want? It wanted the acceleration. Okay, so now I've done the vector sum of all forces. Okay, so I found F net that way, but I have to remember I can also calculate it this way. And now that I have F net, I can calculate acceleration. So acceleration will be the net force, my 40.927, divided by the mass, okay, which they told us was, what, 10 kilograms? 15 kilograms. All right, so we'll take our 40.927 and divide it by 15 kilograms, and we'll get our acceleration in meters per second squared. So all right, so our acceleration is, what do we have, two significant figures there? 3 significant, no, 2. The 35 is only 2. Okay, so we're looking at 2.7 meters per second squared at 48 degrees above the x-axis. Okay. This is where we have to remember that one sentence that was back in the notes a little ways. The force and the acceleration are always in the same direction because one causes the other. Okay? I can't push something north and have it accelerate west. Okay? It has to accelerate in the same direction as the net force. Okay? So that one's a little bit more involved, but nothing you haven't done before. Okay? It's just vector addition. Okay, questions on how that one worked? Okay. All right, so that's all the work that we just did, just typed out a lot neater than my printing. All right, so we just did that. We just calculated the acceleration. Now do this part. Very common for you to get a part B like this. So very often in this unit, guys, you're going to get like a net force Newton's second law question, and then there'll be a part B, and in the part B, you're going to have to switch gears. Okay, you're going to have to go back now, in this case, to a kinematics problem. Right? We just calculated the acceleration of the block, and we found the acceleration of the block was 2.7 meters per second squared at 48 degrees above the x-axis. Right? That's what we were told. Okay? We now want to find out what's the displacement of the block after 8.0 seconds if it started from rest. All right, well, can I do that? Do I have a formula that'll do that? Sure I do. Okay, I've got this formula from back in the last unit. D equals VI times T plus 1/2 AT squared. Okay, I have all of those numbers. Since VI is 0, it's just 1/2 AT squared. So 1/2 times 2.7 times 8 seconds squared. All right, 86.4, but we only have 2 significant figures there, so it'll just be 86 meters at 48 degrees above the x-axis. This is where people would lose marks because they would forget that they just calculated displacement, which is a vector quantity. Okay? If it's accelerating at 48 degrees above the x-axis, its displacement will also be that direction. Okay, something else to notice here, guys. I did not use the full value when I did that calculation because part A and part B are separate calculations. Okay? I finished the calculation for part A. My answer for part A can only have 2 significant figures. Therefore, any calculations I do with that number can only be as accurate as that final rounded number. Okay, so when you're moving from a part A to a part B and you have to use a number from part A, use the rounded answer value. Okay. All right, questions on how that one worked? Okay. All right, so we're going to go over a couple more examples here just to kind of reiterate things and make sure we understand what's going on. Then we'll try a few of the simpler Newton's second law stuff, and then over the next few days, I'll be introducing you to more and more, let's say, I don't want to say intuitive, they're not, but say more complex ones that will require you to think a little bit more. Mathematically, they don't get a whole lot more difficult. Okay, the math stays about the same. Okay, but it's the seeing into the question, being able to decipher the situation, reading a question carefully. Okay, all of that stuff starts to become very important. Okay, so I have a lacrosse player who exerts an average net horizontal force of 3 newtons forward on a 15-kilogram lacrosse ball while attempting to pass it. Calculate the average horizontal acceleration of the ball during the passing attempt. What did they give me in this question? They gave me net force. Okay, what else did they give me? Mass. Okay, and we want to find the acceleration. This is about as easy as a Newton's second law problem could ever be, because they actually gave you the net force here. You didn't have to use the vector sum of all forces to calculate it. Okay, so F net equals m times A equals F net divided by m. Take our 3 divided by 0.15, and we should get 5 meters per second. Is that right? Squared forward. Is that right? Is my math okay on that? I could be wrong there. Hang on. Check my math. Oh, okay. Yeah, I'm totally wrong. 20. What am I thinking? And what do we have here? We only have 2 significant figures, so it'll just be 20 meters per second squared forward. Okay. All right. Don't expect to get very many like that one. Okay. Try these 2 here. Okay. The answers are in brackets, okay, underneath them. So just give those 2 a try, and you'll know if you did them right. These are very, very easy. Okay, these 2. All right, so like I said, these are, again, about as simple as Newton's second law problems can get. In question number 1, they tell us the net force acting on a 6-kilogram grocery cart is 12 newtons. So all we're doing is calculating the acceleration. So acceleration is net force divided by mass, 12 over 6. It's 2 meters per second squared, and that is left, because that's the direction they give us in the question. Again, don't forget little things like that, because it costs you a mark if you forget the direction. All right, and then the second one, a net force of 34 newtons forward acts on a curling stone, causing it to accelerate at 1.8 meters per second squared forward on a frictionless ice sheet. Calculate the mass of the curling stone. All right, so F net equals m times A, so m equals F net over A. So we take our 34 and we divide it by 1.8, and we should get 19 kilograms as our answer for the mass. And that would have no direction because mass is a scalar quantity. Okay, questions on those? All right. Write this one down and give it a try. It's also not overly difficult. Everything's collinear, okay, so you don't have to worry about any trigonometry or anything, but give it a try. All right, let's look at the free body diagram for this one. Okay, relatively straightforward free body diagram. The only trick here is that we have to remember to add the mass of the athletes and the canoe together, because all of that is being accelerated, not just the canoe. Right, so we have 65, 85, 155 kilograms, okay, as our total mass there, the 2 athletes as well as the canoe. And then we have that one athlete is rowing forward with 400 newtons. One athlete is rowing forward with 420 newtons, okay? And there's a resisting force in the water of 380 newtons acting straight backwards, right? So there's my free body diagram. I don't need to draw a vector diagram here because they're all collinear, but I do need to do F net is the vector sum of all forces. So 400 plus 420 minus 380, okay? So we got 440 newtons, okay, and that's going to be forward. That's our net force. From there, we can calculate the acceleration, F net divided by m, and again, you did sum of all forces, and then you did F equals m times A. So we have 440 newtons divided by the mass, which was 155 kilograms. Okay. All right, so we got 2.84. Actually, yeah, we only have 2 significant figures because the mass of the canoe was given in 2. So 2.8 meters per second squared forward. Okay. Questions on that one? Okay, this is one where you really have to read the question carefully. There's a lot of extraneous information in this question. Okay? The reason we give you questions like that is because it's an important skill for you to be able to read through a question and discern what do I need and what do I not need. And there's a fair amount of what you don't need in this question. Okay? So read it carefully, get yourself a free body diagram, right, and see if you can get it from there. So there's extraneous information in this question. The first sentence is completely useless. It only serves to confuse you and give you a piece of information you should not use. It says in here that the maximum mass of the bobsled with 2 riders, a pilot, and a brakeman is 630 kilograms. Then it goes on to tell you that in this question, the 2 guys are still outside pushing. Only the pilot and the brakeman are in the sled. So the mass is not 630 kilograms in this situation because the 2 guys pushing are not in the sled yet. Right? That's where you have to really read a question carefully. Okay? So what we have, okay, is the bobsled, and we have to calculate its mass. So the bobsled's 225 kilograms. Okay? This is going to be 323 kilograms. Okay? And then 420 kilograms. Right? So our mass of the bobsled is 420 kilograms because we only have the sled, the pilot, and the brakeman inside at this point. Okay? Then we have the forces involved. Okay? The forces involved are the 2 sprinters, okay, that are pushing the sled. This is where like Olympic caliber sprinters who don't make it in the Olympics go when they can't make the sprinting team, they become bobsledders. Okay, just about every bobsledder, okay, that you see are guys that were sprinters whose top speed wasn't quite good enough, but they had incredible power. Okay, and that's what you need in the bobsled. It's just guys with big, strong legs who can accelerate the bobsled over a very short distance. So these are guys who can run the 40 in like nothing. Okay, very, very powerful. So they've got guys who are exerting incredible forces of 1,200 newtons and 1,220 newtons. Okay, so extremely powerful. Okay, and then we have a force of friction acting backwards of 430 newtons. All right, now what we have to do now is do our vector sum of all forces. Okay, so we got 2,420, 1,990. Yeah. Okay, so 1,990 newtons, okay, is our net force, and that's forwards. To calculate the acceleration is F net over m. Right, so that'll be our 1,990 divided by the correct mass, 420, and that will give us 4.4 meters per second squared forward. Is it 4? Oh, okay. Do I have a typo on there? Yeah, maybe I have a typo on there. That could happen. 0 divided by 420. 4.7, you're absolutely right. So I got a typo on here. Should be 4.7. Okay, making sense to everybody? All right, so again, really important to read the question carefully so we're sure we use the right mass, okay? And we're getting then obviously the correct answer from there. Okay, elevator questions. Elevator questions are one of the easiest and most common Newton's second law problems. Mathematically, very, very easy. People always forget something, though, when they're dealing with an elevator. Okay? That something is they forget gravity. They just focus on the forces of the elevator and forget that the elevator is there to help counteract gravity. That's its whole purpose. So don't forget about gravity. Okay? Now, I say elevator question. In this case, it's actually an elevator. But any object thrown vertically is technically an elevator. Right? Because we're only considering the time where the force is actually acting on it. So throwing a rock up in the air is actually an elevator question. So people tend to not forget gravity when it's an elevator, but they forget it when it's an elevator that's actually a rock. Okay? Then they forget that gravity is involved and they just focus on the throwing force and they forget that the throwing force is counteracting gravity. So always remember, in any elevator type question, gravity is involved. All right? Now, give this one a try, see how you do on that. Remember that the formula for calculating the force of gravity we learned yesterday. It's mass times the acceleration due to gravity, which if you're not told otherwise is 9.81 meters per second squared. Okay? give you a few minutes on that one. Okay, so if we're looking at this one, first thing we need to do is kind of modify their free body diagram because it's not including all the stuff we would normally put in it. Okay, the mass is 600 kilograms, right? The tensional force, okay, the elevator cable is exerting a force of 6,500 newtons up, okay? And then we have to calculate the force of gravity. So that's going to be 600 times 9.81, which is going to be 500 what? 5,886, sorry. Yes, 5,886 newtons. Okay, so there's our force of gravity downwards, 5,886 newtons. Now, what's my next step? If I'm going to calculate the acceleration I need F net. All right, so F net is, as always, the vector sum of all forces. So 6,500 newtons minus 5,886 newtons, because they're in opposite directions, is going to give us 614 newtons. Is that right? Yeah? Okay, so 614 newtons, and that is in an upwards direction. So now I can calculate the acceleration. It'll be F net divided by m, right? 614 newtons divided by the mass of the elevator, 600, right? And we should get like 1 point something there. Okay, so 1.02 meters per second squared. Okay, and we don't want that acceleration to be really big. Okay, an elevator needs to have a comfortable rate of acceleration. If it accelerates upwards too fast, it'll hurt people's legs. Okay, like it'll buckle your knees if it accelerates upwards or downwards too fast. You probably all had that sensation sometimes in an elevator where the brakes release, but it takes a second for the motor to catch, and it feels like you're free falling for like a half a second. Okay, yeah, well that's really what's happening because the motor hasn't caught up yet, right? And you know, it can be dangerous. Obviously, you don't want to fall in an elevator. Okay, well, I mean it's no different really than falling any other way, but in an elevator it's worse. I don't know. Don't fall in an elevator. Bad. Okay. So, like I said, elevator questions, when they're an elevator, people don't forget gravity, okay? But if it's a rock thrown up in the air or something like that, people forget about gravity all the time. Anything moving vertically upwards as a force question, gravity's involved, okay? Always remember it. Okay, so same person in this as in the example rides in the same elevator. All right, so remember that the elevator and the person together had a mass of 600 kilograms, right? So we'll need that. Now the cable elevator exerts only 5,200 newtons worth of force. Find the acceleration of the person, right? Then we'll talk about number 2, okay? Because number 2 is a little bit different than this first one. Maybe we won't get to 2, we'll see. Okay, so let's have a look at question 1 here. So it's same elevator, same person, okay? So we have this 600 kilogram elevator. Now we know that the force upwards is only 5,200 newtons. Force downwards is the same as before because it's still the same elevator and the same person, 5,886 newtons. So which way is the elevator going now? Downwards, okay? And this is how an elevator lowers, right? It just exerts less force upwards than it did when it was actually lifting, so it doesn't have to work as hard. So when we do this, we're going to have 686 newtons downwards as our net force. Okay, and that's going to be down. So now we can calculate the acceleration, 686 divided by 600. And when we get there, 6.1, or sorry, not 6.1, 1.1. Oh, sorry, it's right here. 1.14 meters per second squared. Okay, and don't forget the down part. Okay. All right. Question number 2 is trickier. Question number 2 has to be solved by what we call the differential acceleration method. It's a really complex name, but it's actually not that hard a process. In order to solve number 2, here's what we have to understand about calculating any force. We've already said that net force is mass times the overall acceleration. Okay, the mass of the entire system, all the objects involved, times the acceleration of the system. We can calculate any force that way. We've already looked at how gravity is calculated by going mass times the acceleration due to gravity. right? So we calculate any force that way. We take the mass of the object and multiply it by the acceleration that is produced. Okay. So when we're looking at number 2, it says we have an electric chain hoist that can exert this much force upwards. Okay. It's lifting an engine to remove it from a car. They tell us the acceleration of the engine, but they don't tell us the mass. All right. So that's a bit of a problem, okay, considering that gravity is one of the forces involved, and the only way to calculate gravity is to have mass. Okay. It's going to make it a little harder for me to calculate the net force if I don't have any way to calculate one of the forces that's involved here. All right, so we don't know the mass of the engine. What we do know is that this force upwards is 2.85 times 10 to the 3 newtons. All right, everybody okay with that? All right. So if I'm looking at doing the vector sum of all forces for this question, which we already said we can't really do, okay, I would have F net equals the force of the hoist, which I know, plus the force of gravity, which I can't calculate. But really what I'm saying is mass times acceleration equals mass times the acceleration the hoist could produce, plus mass times the acceleration due to gravity. Right? Is that essentially just rewriting the same equation? Okay. What's in every single one of those terms? Can I get rid of it? Okay, now I know what you're thinking, Coder. You're supposed to calculate the mass of the object here. Why are you canceling it? I'll get to that. Okay, for right now, I want to eliminate it. What we have to realize here is that adding forces together gives us net force. Well, acceleration is the same. It's a vector quantity. If I add all the accelerations together, I can get the net acceleration. Right now, you're probably also thinking, Coder, they told you what that is, doofus. You already know that. Okay? Yeah, I realize that. Which one do I not know the acceleration of? I don't know the hoist's acceleration, right? But I can calculate it, and since I know the force of the hoist, can I find with the force and the acceleration the mass it's lifting? I'm going to kind of work backwards here. All right, so what I'm first going to do is solve for the acceleration of the hoist, because I know the acceleration net. I know the acceleration due to gravity. So I'm going to calculate the acceleration the hoist can produce by itself. If there was no gravity, how much acceleration could the hoist produce? All right, so AH is going to be the A net, okay, minus gravity. Now, that gravity is going to have to be negative, so it's actually going to be minus negative 9.81 here. All right, so I have that the acceleration of the hoist is 1.5 meters per second squared up minus negative 9.81 meters per second squared. So this should sort of make sense. The acceleration of the hoist has got to be bigger than gravity. Otherwise, it's not lifting anything. Agreed? Okay, so if I take the 9.81 and I add 1.5 to that, because that's essentially what we're doing, okay, there's the acceleration that this hoist could produce if gravity wasn't there. Right? It would be able to accelerate the object at 11.31 meters per second squared. Now that I know the acceleration of the hoist, I can do this. Mass times the acceleration of the hoist equals the force the hoist exerts. And I know that number because they told me what it was in the question. Okay, so now I have the acceleration produced by the hoist, the force of the hoist, and now I can calculate the mass. Okay, so mass will be force of the hoist divided by the acceleration of the hoist. Okay, so 2.85 times 10 to the 3, okay, divided by our 11.31. Okay, so the mass of the engine is 2.5 times 10 to the 2, right? We only have 2 significant, no, we have 3. So 252 kilograms. Okay, which is 580 some pounds. Okay, heavy. Yeah. All right, it's not often that you run into a question where you have to use the differential acceleration method. In fact, I can't remember the last time I put one on a test, so I probably never have, probably never will, but it's still important to understand the relationship here, and that is that if the vector sum of all forces is the net acceleration, the vector sum of all accelerations is the net acceleration. Okay, that relationship holds true because they're all linear, right? They're linearly related or they're directly proportional. All right, we'll leave it at that for today. We'll look at some more stuff tomorrow.